Welcome to this video that explores the integration of inverse circular functions. Now, what we're going to investigate is actually how to integrate certain expressions that lead to inverse circular functions. So if you can see here in this table, this is the antiderivative. So capital Fx actually stands for the antiderivative. And you've got three different forms. So you've got this form here, and this form here. Now, if you remember back from our differentiation skills, when we differentiated sine inverse, we got that expression as the derivative. Now what we're doing is we're looking at how we can go from the derivative back to the original expression, because remember that we're integrating this time. So when we went from the expression fx to f dash x, we of course were differentiating. Now we're looking at anti-differentiating. So anti-differentiation always has this integral sign in front of it and dx at the end, or whatever variable you have within this expression. So we're looking at anti-differentiation. And also there's a domain associated with the values of x. And the reason why is if we look at the denominator here, we can see that there is an x value on the denominator, which means that essentially not every value of x can actually be included, because remember that x being on the denominator means that there is some kind of restriction to what x values are allowed to exist. So because there's a square root there, you can't have an x value that will yield a negative total at the bottom of the denominator, because that will mean that you can't square root a negative number. You also can't get 0 on the denominator, so that will also influence what values of x you can and cannot have. So we'll look at that and explore that a little bit later. But first of all, I think the trickiest part of all of this is actually understanding when you have the forms. And basically remember that in an exam situation, you will not be told that you're looking at a circular function expression, and so an inverse circular function expression. And so it's really important that you just recognize when it's appropriate to use these, because these questions will be all mixed together. Okay, so let's have a look at the examples, because really up there we have different forms and they may not necessarily mean anything right now. So I want to start off with an example to show you how to sort of work this out. So it says find an antiderivative of the expression, and here we have it. Here it's 2 divided by square root of 9 take away x squared. So if I set this out properly, I'll have the integral of 2 divided by square root of 9 take away x squared, and I'll put a little dx at the end. Have to do that. This tells me where I stop my integration, and it also tells me the variable that I'm integrating. So it's very important to have that dx at the end. Now I can see that this is probably, it looks sort of like this form here, except obviously there are differences in it. There is a 2 at the top. So what I can do is, the first step that I can take is I can just remove that 2, put it outside of the integral, and just leave it as 1 over square root of 9 take away x squared dx. There we go. So now that's looking a little bit more like the very first expression that we have up there. And so we can see that a squared is 9. Okay? So what we can do is we can straight away go into the actual expression. So we can say 2, and then we can see that there's a positive number at the top there. So that's probably sine inverse. Right, sine inverse, and then we just put x at the top divided by a. Now, a squared was equal to 9, because this is in the form of a squared take away x squared, so a is actually 3 in this case. We don't worry about the minus 3, we just take the magnitude of it. Okay, and then you've got the plus c. Sure, I might just leave to the, well, we can put it in right now, say plus c1, like so. C1 just means some kind of constant. And then we're going to just expand that 2 outwards. So we've got 2 sine inverse x over 3 plus c. Now we're just going to turn this 2 multiplies the sine inverse first, and then the 2 multiplies the c1. And I'm just going to say that the constant c is equal to 2 times c1. It doesn't matter what you make the constant. This is going to simply be a number, and I've made that entire number the letter c. Okay, so that's an antiderivative. Now, an antiderivative means you just have to worry about finding 1. You don't have to worry about finding the entire expression, so really you don't even need that plus c. C can be 0 in this case. So a suitable answer would even be sine inverse of x over 3, where c is 0. Okay, so that's our first antiderivative of the expression. So let's have a look at the second example. Now, in example number 2, we can see that we have a negative expression. And so a negative expression indicates from our table up here, when we have a negative in front of our expression, I'm just trying to find the mouse. Okay, great. So when we have a negative here, we can see that it relates to a cosine inverse. And so in this example that we have down here, this is going to be cos inverse, most likely. And so I'm just going to write this up again. So we'll find the antiderivative of minus 5 over square root of 36 take away 4x squared dx. And what I'll do first is I'm going to, I can take out just a 5. I could take out negative 5 too and turn it into a sine inverse, but I'm going to keep it as a cos. They are interchangeable. Okay, so I've got this expression. Now, the denominator looks right, except there shouldn't be any number in front of your x squared. And in this case, obviously there is a number in front of x squared. So what I'm going to do is I'm actually going to take that number out. So I'm going to go minus 1 over, take out square root of 4, and what you're left with is 9 take away x squared dx. And so that's going to be 2 at the denominator, and once again I'm going to take it out. So it's 5 over 2 minus 1 over 9 take away x squared dx. So essentially I've just taken out the number 4, and I now have the correct form that you can now apply the integral formula to. So let's have a look at how to do that. So we know that, again, in this case, a squared is equal to 9, and so a is simply 3. And when we use our table, we know that we will be dealing with cos inverse of x on 3 plus c. And again, because it says an antiderivative, it's okay to make c 0 or any number You're just finding one antiderivative. So you've got this expression. Just to keep it simple, I've chosen to make c equal to 0. Okay, so let's have a look at this next example. So this next one looks a little bit more like the tan expression. So going back to our table, we can see that the tan formula has an a squared at the bottom and an a at the top. And so that's a very important setup. And let's go back to our actual question here. So there's a few things that are a little bit different in this example. So it should be a over a squared plus x squared. Integral of that will give us tan inverse of x over a plus c. We again want an antiderivative, so I'm just going to assume c is 0. But yeah, there shouldn't be any number in front of our x squared there. So first of all, first step, I guess, I'll just write this expression out. Okay, I'm going to actually take out both a 2 from the top out, and I'm going to take out that 4 from the denominator. That will leave me with 1 over. Now, because I've taken a 4 out from that expression, there's going to be 9 over 4, because I've taken out a 4 dx. Okay, so that's going to be half 1 over 9 over 4 plus x squared dx. Okay, so we've got this expression so far. Now, a squared is actually equal to 9 over 4 this time. So a is equal to 3 over 2. And so we've got 1 at the top, but we really need 3 over 2 on the top there. And so what we're going to do is we will introduce 3 on 2 and place it at the top there. I'll just find a different color. Where is my... Okay. So we do need a 3 on 2 at the top there. So I'm going to times this by 3 over 2. We can't simply just introduce a number into an expression. It's actually not mathematically correct to just say, okay, we need a 3 on 2, let's just multiply 1 by 3 on 2. We actually do need to then balance it out and return the expression back to what it was by doing the reciprocal, doing the inverse. So multiplying the outside number by 2 over 3. Because essentially what will happen when you introduce 3 on 2 on the numerator there, and you introduce 2 on 3 as the outside number, they will actually multiply by each other, and essentially they will create 1, which will make no difference to the overall expression. But yet it's useful in the sense that now we actually have the value that we need on the numerator to solve the problem. And so it's all about thinking about how to introduce that number but yet cancel it away at the same time and make sure that you're not changing the value of the expression. So let's have a look at how we would solve this. So the 2 and the 2 here cancel. That would give you a third. And you've got 3 on 2 now at the top there, all over 9 on 4 plus x squared dx. So we've got everything we need. We've got this kind of format. Okay, and so all we need to do now is we just need to use our rule. So a third tan inverse x over a. A is actually 3 on 2 plus c, but we decided that we're going to make c 0. The final way to express this would be tan inverse of 2x over 3. So that will be our expression. Okay. Now let's have a look at example number 4. So it says, once again, it looks like a tan form. Find an antiderivative of this. Okay, so once again, we're trying to okay, so we want to remove 16 from outside of x, and we want to also remove this 3, because it might block us from being able to figure out what number is appropriate at the top there. So 3 over 16. There's 1 left over at the top, and then there's 9 over 16 plus x squared dx. Okay. So now what we do is we have to, the top number up there has to actually be, in this case, a squared is equal to 9 over 16. And so a is equal to 3 over 4. And so we need to multiply the top by 3 on 4. And what we do to the top, we actually have to reverse that on the side here, 4 over 3. Okay, so finally, these 3's here will cancel, and you actually get a quarter integral of 3 over 4, 9 over 16 plus x squared dx, and that gives us 1 over 4 tan inverse of x over 3 on 4 plus c, which is 0, and so therefore it's just going to be a quarter tan inverse of 4x over 3. So that's our antiderivative. Okay, let's have a look at this expression, this example here. This is our final example of the tutorial. Let's have a look at how to do this one. So find an antiderivative of the expression this. Again, we have a negative there. So it's we can just turn it into a cosine. We need to take the 3 out. And it would also be useful to remove this 2 from in front of the x squared. So as I remove that 2, I have to divide each of these terms in there by 2. So I've got 5 over 2, take away x squared. And so that gives us, what I'll do is I'll take this third here and I'll actually remove it. So 3 over square root of 2. Here we get that expression. And then I'm just going to move it up here. So I might rationalize that denominator actually. Okay. And I'll actually remove this. So a squared in this case, a squared, the number is here. So a squared is actually 5 over 2. So a is square root of 5 over square root of 2, which as a rational as a rational number, to rationalize this particular third, we have to multiply it by square root of 2. So we've got 2 square root of 10. Okay, so that's our value of a. So we now go cos inverse of x divided by a being square root of 10 over 2 plus c, which we're going to make 0. We flip that number around, so 2x over square root of 10. And now we're just going to also, it might be worthwhile to try to rationalize that denominator there. By multiplying by square root of 10. And so this and this will cancel, that will give us 5. And so our final integral will be this value here. Okay, now what I didn't describe was the domain. So you can see that the original expression has a denominator of square root of 5 minus 2x squared. And we know that the content within that has a bit of a restriction. First of all, it cannot be 0. Can't be 0 because it's a denominator. Secondly, the content within that bracket has to be positive. Has to be positive. Okay, so there are two restrictions on that particular denominator. And so if we just take away the square root and think about what this graph is, we can see we're dealing with a parabola. So I'm just going to draw an image of a parabola of this particular form. So we've got the parabola, we've got a negative parabola that's moved up by 5 units. So here's our parabola. So I'm just drawing out the function y equals to 5 minus 2x squared. And I know that this point and this point we can find what they are. And that's by making the y value 0. So we just work out that it's 5 over 2 equals to x squared, and x squared is equal to what we had right here. So, well, x is equal to square root of 10 over 2, and it's actually plus or minus. This point here is going to be plus square root of 10 over 2 and 0, and this point here is minus square root of 10 over 2 and 0. And then that point up there is just going to be 5. Now, the region of what we're looking for in this problem is we're actually trying to find both the x value for which we won't get 0, and also it has to be positive. So we're looking for all of these values up here. So there is a reason for why the domain equation was what it was. And you can see that the domain in this case, x would have to be an element from this value up to that value, because all of these values up here would give you a positive parabola. So it's positive y values up there. So in order to make the content positive but not allow the content to be 0, remember that we're inspecting the y values here, and so the y values have to be positive, but yet they cannot be 0. So x values have to be between negative square root of 10 over 2 up to square root of 10 over 2, but not inclusive of them, because when you include them, the y value becomes 0. The moment the y value becomes 0, this whole denominator here will be 0, and you can't actually have a defined function. So this is why the rule in the table says that to find the domain quickly, you can avoid drawing these parabolas, you can simply substitute. Your domain is simply between negative a and positive a, and so that's a very handy thing to put into your data book or bound reference. Now for tan is, it's not as fussy as a sine inverse or cos inverse, because tan, it doesn't matter whether the denominator here, the denominator will actually never be 0, because you're squaring your x values, and so it's not possible to get a combination of a negative and a positive number, because you're squaring both a and you're squaring x, and so it will always be positive no matter what x is. And also there is no square root sign, so therefore there is no restriction upon the x values, and so x can be an element of all real numbers. So hopefully that made sense. Stay tuned for the next tutorial, which will be looking at integration by substitution. Thank you.